when we look at more detailed periodic tables of elements, we see that they provide us with both the atomic number, so the smaller of the two numbers, and a mass number. It's also called the relative atomic mass. Now, if these atomic masses are not whole numbers, then that lets us know that there is more than one possible nucleus arrangement of these atoms, and these are called isotopes. The example I've got here is chlorine, and we can see that its mass number is 35.5. Because that's not a whole number, that tells us that there are different isotopes or types of nuclei for chlorine. The 35.5 is the average or the mean of all chlorine atoms that we weigh or take the mass of. So, and the unit is basically one proton has a mass of 1, one neutron has a mass of 1. But we can't have 35.5 protons and neutrons in a nucleus. So it means that there are different arrangements. And actually what we find is that some chlorine has a mass of 37, so it's the heavier one, and some has a mass of 35. And we work out the number of neutrons in those by going the mass number minus the atomic number. That's because the mass number is the protons plus the neutrons, and our atomic number is our number of protons. So if we subtract the number of protons from the mass number, we get our number of neutrons. Now, because chlorine with a mass of 35 is closer to 35.5, we know this is the more common, so the more prevalent isotope. Because 37 is a lot further away from 35.5 than 35 is, we know this one, while it exists in a good amount, is less common. We find that it's about a 3-to-1 ratio. For every 3 of these, we'd find 1 of these. Another good example would be bromine, another what we call halogen or group 17 element. So again with 7 valence electrons. The two most common isotopes of bromine, and they're nearly in a 1-to-1 ratio, there's nearly 50% of each, is bromine 79 and bromine 81. So, I haven't done the answer on this. You would go though, 79 minus 35 to find the number of the number of neutrons in this one. And you'd go 81 minus 35 to find the number of neutrons in this one. They are chemically pretty much the same. They have the same electron configurations, so in chemistry, we don't treat them as being any different. They react the same way. But it is useful to know because the nucleus, a heavier nucleus, of course, will mean that it needs more kinetic energy to move just as fast as a lighter nucleus, so therefore there would be some effect, subtle effect in the rate of reaction. And these isotopes become really useful when we look at nuclear physics and nuclear chemistry, and that's more heading down. Nuclear physics is probably level 2 and level 3, and nuclear chemistry, we're really getting into university level learning there.